This is lesson 9 in the force and motion topic entitled Levers and Gears. Once again, this is for triple award students only. And during the course of the lesson, you should be able to recall that levers are so-called force multipliers. Recall that gears can be used to produce a large or small turning effect, and understand the situations where different types of gears are used. Okay, because this is related to the moment's work, let's just pause and see if you can have a go at answering these questions without looking back in your notes. So if you'd like to pause the video, answer those questions and we'll go through them in a moment. Okay, hopefully you didn't find those too difficult. First off, what is the turning effect of a force called? It's called the moment of the force. Examples of units, it's got to have newtons at the start and then any unit of distance you like. Say that is probably the most common, but that's usually the most useful. Calculate the turning effect of a 30 cm spanner that is used with a force of 60 newtons to undo a tight nut. Moment equals force times distance, 60 times 30, which is equal to 1800 newton centimeters, or if you were to change that into meters to 0.3, it would give you 18 newton meters. State the rule that tells us whether or not a seesaw is balanced. It is the law or principle of moments, which says the total clockwise moments must equal the total anti-clockwise moments. And finally, state whether or not the seesaw will balance. Justify your answer with the calculation. Well, applying the principle above, anti-clockwise moments must equal clockwise moments if it's to balance. 1 times 2 plus 1 times 1 is not equal to 1 times 4. So 4 is greater than 3, so it will tip in a clockwise fashion. Today's lesson is going to be about two simple machines, levers and gears. Okay, as ever, this has to be in your notes. You put the title levers. Okay, so levers use small forces to move much larger forces, so they're often referred to as force multipliers. Let's take a look at the most common type of lever. It's a crowbar, and the crowbar here is being used to lift quite a substantial heavy safe with quite a small amount of effort, and we'll see why that is. So on this side here, because the man's force is applied quite a large distance from the pivot here, in order to get that safe to balance, the large distance here, small effort here, means, by the principle of moments, that it could balance the larger weight here, the small distance from the pivot here. Okay, so it's possible for a small force at a large distance to balance a large force at a small distance, and that's the operating principle of the lever. Okay, so have a look at the detail in this question here, pause the video, make your note and see whether you can answer the question there. So the question is asking how much force would be required for the man to lift that 500 newton safe. Okay, for it to balance, just balance in that situation there, then anti-clockwise moments must equal clockwise moments. So his force, is applied 0.95 meters away from the pivot, or 95 centimeters, and that must equal 500, the weight of the safe, multiplied by its distance from the pivot, 0.05 meters or 5 centimeters. So if we multiply that out, we get 25. The effort therefore is 25 divided by 0.95. So it's possible for that man to balance that safe by using just 26.3 newtons. Apply a little bit more and he'll actually start to lift it and move it. So you can see here that the crowbar has done its job. It's reduced the amount of force that he has to use to lift a much heavier one. It is a force multiplier. Make sure that you pause the video and you get that complete note. Other examples of levers, you quite often overlook the fact that the door handle is always placed a long distance from the pivot, from the hinge there, so it makes it easier to push or close the door. Large handled spanners are used to undo very tight nuts, or tighten them, because you've got this larger distance from the pivot, the nut itself, which allows you to create a greater turning effect. And opening a tin of paint is always easier using a screwdriver, because you've got a little pivot here. You're applying a force a large distance from the pivot, and therefore it magnifies your turning effect. Okay, also for your notes, could you put the title gears, and you will need this slide. It's a little bit complicated to draw, I appreciate that, but it's just not easy to do anyway. So first off, gears are usually a pair of spinning discs of different diameter that are linked together by cogs. You've all probably experienced gears on your bike or on a hand-driven food mixer or a drill. So we have, in this case, a set of gears whereby this side here is where you apply the effort. So you could have a handle on there, as it were, turning that, and your force is transmitted over to this second set of cogs here, the driven, as it were. So this is where you apply the effort. That is effectively the load. Now, if you apply a force of 100 newtons here, you're turning the handle here, you're effectively creating a moment of 100 times 10, because that's how far you're applying it from the pivot there. However, because the drive has got a larger diameter, 15, if you work out the moment on this side, you've got a larger moment. So the moment of the driver is 100 newtons times 10, 1000 newton centimeters, but on this side, because you've got the larger diameter cog, you've got 100 times 15, so the moment of the force is greater. So you've got again your force multiplier here. Now, as ever, you're not getting something for nothing here. The disadvantage is that the driven disc actually rotates more slowly. So if we put some figures to that, if that has 20 cogs on it, the driver, and the driven has 30 cogs, then when the driver has completed one complete rotation, the driven still needs to complete another 10 cogs to complete its revolution, i.e. it's moving at around about 2/3 the speed. So this situation you've got here increases the turning effect, increases the turning force, but reduces the speed of the output. Please pause, have a think about that, and get that into your notes. Okay, so a nice little summary again for your notes. The top gear here on the right hand side is what we term a low gear, and that's when we use a small gear to drive a large gear. We saw that in the example a few moments ago. The speed of the output is smaller, so this moves more slowly than the driver, the one that you're turning, but the benefit is that we get an increased turning effect, a greater moment. So our turning force is effectively multiplied. In a high gear, you've got the opposite situation where a large gear turns a small gear. This time, the output, the driven, is much faster than the driver, but you lose that advantage of having that greater turning force. Okay, so think about the properties of these two sets of gears. When do you think a cyclist would use a low gear, and when do you think he'd use a high gear, given the explanations here, the descriptions here? Pause the video, have a think about that, answer it in your notes. Okay, hopefully you got that. No need to write this into your exercise books, just study the statements there and select which of the two options in each case is correct. So pause the video, have a read of that, and I'll go through the answers in a moment. Okay, so in a low gear, a small gear turns a large gear. The speed of the output is smaller, but the output force is larger. And that's ideal when you are trying to go up hills or start your bike off to begin with. In a high gear, a large gear turns a small gear. The speed of the output is larger, but the output force is smaller. And this is used for cruising along, going along at high speeds. Please take a moment to review what we've learned today.